Welcome to Hi-Fi, a high-yield physics lecture series to help you become a better radiation oncologist and help you pass boards. In this video, we're going to be talking about penumbra in photon beams. First, what is penumbra? Penumbra means almost shadow, so in other words, the blurred edges of the photon field that are almost but not completely blocked. There are three types which combine to create the penumbra we see in our photon treatment fields. The transmission penumbra through the edges of the collimators shaping the field, the geometric penumbra from the size of the radiation source, distance from the source to the collimator, and distance from the source to the skin, and the radiological penumbra from the scattering of electrons generated inside the photon field. Throughout this video, we will refer to a source of radiation with a size S, and collimators, which may be multi-leaf collimators or jaws. These are arranged at a source-to-collimator distance, or SCD, also referred to as a source-to-diaphragm distance, or SDD. Finally, all of this is in relationship to our patient by the source-to-skin distance, or SSD. These factors interplay to give us a penumbra of some width called W. To show you what we mean, let's start out with what a perfect photon field without penumbra would look like. Let's draw a megavoltage source here, where the photons come out. For now, let's imagine that it's a tiny point of negligible size. Here is our collimator. This can be a multi-leaf collimator or a jaw that creates the photon field size and shape. The photons come out of the source like this to create the beam path. These are the edges of the beam. Now let's bring in our patient, zooming into the skin surface, which is set up at some distance from the source. Let's draw what the dose profile would look like across the patient at the patient's surface. We start out at a low dose leading up to the edge of the field. Then it jumps up to 100% dose within the beam, stays pretty even across the field, then drops back down at the other edge of the field. This is an idealized dose distribution of what we would see if we had no penumbra, with sharp falloffs at the edge. This is what we call a step function in physics because it only steps straight up or down. Now let's think about what happens in a real situation. First of all, you might notice that the collimators drawn here don't exactly match the divergence of the beam. This means that the edges of the beam are passing through different thicknesses of collimator material. The parts of the beam that pass through more of the collimator are blocked more and attenuated more, which means less photons go through. The parts of the beam that pass through less of the collimator are blocked less and attenuated less, which means more photons go through. This effect is called transmission penumbra, because it's created by the dose being transmitted through the ends of your collimator. The effects of transmission penumbra are reduced with collimators that have ends which match the divergence of the beam. But there are limitations in LINAC design, because the collimators can't match the beam divergence exactly for every field size. An additional design feature is having a rounded edge MLC rather than a square edge. This keeps transmission penumbra relatively constant, independent of leaf position. Regardless of its position, with a rounded leaf, the amount of MLC material the beam passes through is relatively constant. Now let's look at a real source. A real source is going to have some finite size S, which is going to have an effect on the beam. The center of the source is unobstructed by collimators. Photons originating from here will proceed down from the source to a point in the patient. As you move toward the edge of the field, the situation changes. In particular, as you get right toward the edge, the jaw starts to shield part of the source. For example, you can see that the right part of the source is occluded as you get close to the field edge, because this part of the source is blocked. So here, the dose is a little lower, and it drops as you get near the field edge. Now let's consider what happens outside the field. In the ideal case, a dose outside the field is basically zero. But what you can see is that at this point, you can still see part of the source. The dose is still kind of high right at the field edges, and then it trails off as you get farther out. So this is the final result. It's not a sharp falloff, but it's smeared out. This is the geometric penumbra, because it's created by the geometry of the source size, the distance from the source to the collimator, and the distance from the source to the patient. Now let's take a look at how geometric penumbra changes with source size, SSD, and SCD. You'll see that S projects down here through the edge of the collimator and diverges. If we set up the patient here, there's going to be some penumbra width W. If the source was small, as in our idealized scenario, the penumbra would be small. As we increase the size of our source, the penumbra increases. If we increase SSD by moving the patient farther away from the source, you'll see that the penumbra width increases. If we move even farther away, the penumbra width is even wider. So you'll see that the width of the penumbra is larger for larger SSD setups. If SSD is constant and we increase the SCD by bringing the collimator closer to the patient, our penumbra will actually decrease. We can attach a formula to this to calculate what the geometric penumbra would be for different distances. We just said that penumbra is directly related to S and SSD and inversely related to SCD. Penumbra is also directly related to the depth of treatment, so our actual penumbra equation looks like this. Now let's look at another effect that contributes to penumbra. When talking about the primary beam, the photons have undergone Compton scattering, resulting in electrons that go on to deposit dose. Some electrons will be scattered within and outside the field and deposit dose within and outside the field. You don't have electrons scattering into the field because theoretically no photons have reached that area, if we're ignoring scatter and leakage. This is also described as lateral electronic disequilibrium. Electrons generated in the beam will scatter outside the field, but there is disequilibrium because there's no scatter coming from the other direction. So that ends up reducing the dose inside the field near the edge and raising the dose in the outside region. That creates another penumbra falloff that is called the radiological penumbra, or scatter penumbra, because it's created from the radiological effect of electrons moving from the place that they're created and depositing dose elsewhere. Radiological penumbra width increases with the energy of the beam because higher energy electrons travel farther. It also increases in lower density material. For example, in lung, because electrons will travel farther. It's all about the range of these electrons. The range of electrons in soft tissue is about the energy in MeV divided by 2, and that will give you the approximate range in centimeters. Now let's take a look at what the dose profile looks like at the edge of our photon field, with penumbra considered. The dose is 100% here near the center, and then drops off at the field edge. To quantify total penumbra, we take the 80% line and the 20% line, and then figure out what the width is. That width is our penumbra. One more point of interest here is the dose at 50% right there. That's how we define our field edge. So if we have a 10 by 10 centimeter field, it's 10 centimeter from the 50% dose on one edge to 50% on the other edge. Another way to say that is the dose drops to 50% at a distance of 5 centimeters from the central axis. Alright, now let's recap how the factors we just covered can increase or decrease photon penumbra. Increasing source size or source to surface distance will both increase the size of geometric penumbra. Conversely, increasing source to collimator distance will decrease the size of geometric penumbra. Increasing beam energy, as commonly used to treat deeper targets, results in a longer range of secondary electrons and therefore a larger radiologic penumbra. Unfortunately, we don't have time to go through sample calculations, but if you need to compare the penumbra of two setups using the same energy photon beam, you can use this equation. And there you go, all you need to know about photon beam penumbra and then some.